Welcome to Computer Science MS5, and in this video we're going to be looking at computer systems, and we're going to be breaking down into what is a computer system, the von Neumann's architecture, secondary storage, main memory, components of the CPU, and the Fetch-Decode-Execute cycle. So quite a bit of content. Bear with me, pause the video, take notes, create flashcards. Use this to help you answer exam questions because there's a lot of information coming your way. So firstly, let's start off with the question, what is a computer system? And you probably would have been asked this in year 7. And we're going to build on the basics and go right through to the real nitty-gritty details of how a computer system works. So a computer system is a combination of hardware and software. So hardware, the physical components that you can touch, and software, the programs. And that hardware and software takes inputs, processes them, and produces outputs. Now, we use computers that are based on von Neumann's architecture, and that's a system where the CPU runs programs, instructions, and data stored in main memory. So both the program instructions and the data are stored in the same place. And that's a picture of von Neumann, and that's one of the original computers that he created using this architecture. And that technology is still used today, but it's much, much, much smaller. So we look at that system, a combination of hardware and software that takes inputs, processes them, and produces outputs. And as we zoom in there, we can see our processes are fetching instructions and data from memory. So this is some of the hardware that we use in our computer systems today. And as you can see, we've got inputs in the form of signals, and they're feeding into the CPU. And we've got these arrows, which we're going to be describing in a bit more detail in a bit, which describe the Fetch-Decode-Execute cycle. So let's zoom in at each of these components and see what they do. So this represents secondary storage. In this example, this is a hard disk drive, which is a type of magnetic storage. Now, the purpose of the hard disk drive is that it stores applications and data when they are not in use. So it's really, really important that I have somewhere to store my homework or all my programs like Google Chrome or Epic Games or Microsoft Office. I need to have somewhere to store all of that when I'm not using my computer. So when I switch off my computer, where is all of that going to be stored? It's going to be stored on secondary storage. Now, some features of secondary storage is that it is non-volatile. It is permanent, and it retains the contents when the power is off. So permanent storage retains contents when the power is off. Those 2 points are the same as saying non-volatile. So if you really, really want to show the examiner that you know exactly what you're talking about, you're going to say secondary storage is non-volatile. It is permanent storage, which means it retains the contents when the power is off. The purpose of secondary storage is to store applications and data when they are not in use. And it's also worth noting that it has a greater capacity than RAM. So it can store more than RAM. So we've just taken a look at secondary storage, which you can see it's all the way on the side there. It's just before this long stick here. And that long stick is known as RAM, which is random access memory. And it is also known as a part of main memory. So its purpose is to hold applications and data currently in use. So it holds applications and data while you're using them. It also holds applications and data that are open. So let's say, for example, I've opened up Google Chrome, and then I click on my Microsoft Word document, and that opens up, and I'm currently using that Microsoft Word document, so that's going to be held in RAM. Now, its features are it is volatile, it is temporary, and it loses its contents when the power is off. So those second 2 points mean the same as volatile. So if you're going for those big marks in the exam, you're going to describe RAM as temporary memory that loses its contents when the power is off and is volatile. It holds data and applications that are currently in use or open. And it has quicker read and write times than secondary storage, but it has less capacity. And a big reason for why we don't just have a lot more RAM in our computers, aside from it being volatile, is that it's more expensive than secondary storage. So when you're thinking about RAM, it's volatile. So imagine I've got my homework open and suddenly I lose the power to my computer. My homework's going to disappear because I haven't saved it. I haven't saved it to secondary storage. It was only in RAM, and that is temporary, and it lost its contents. So we're now going to take a look at ROM, which is another type of main memory, and it is short for read-only memory. And the purpose of ROM is it holds a basic input-output system. Now that system is essential for booting the computer. Another way for saying booting the computer is starting the computer. So when I press the power button, I need to get all the instructions for how the computer switches on from ROM. And now, even though it's main memory, it is actually non-volatile, permanent, and it retains its contents when the power is off, which is really important because if my computer switched off, I don't want it to forget how to switch on again. So the contents are saved. Now, they cannot be changed or written to, hence the name read-only memory, because what I don't want to happen is someone who doesn't know what they're doing to change what the instructions are for booting my system. So ROM is read-only. That's what ROM stands for, read-only memory. So we've looked at secondary storage. We've looked at the first two pieces of main memory. Now we're going to look a little bit closer at the central processing unit, which is the full way of saying CPU. Now the purpose of the central processing unit is to process. It processes all data and instructions that make the computer work. So anytime you switch on your computer and it does something, it's a central processing unit that allows that to happen because it has to process. It has to do all the work inside the computer. And it does that by fetching, decoding, and executing instructions that are stored in main memory. And we're going to look at the Fetch-Decode-Execute cycle in a bit more detail in a bit. Now, some features of the CPU is its performance is affected by clock speed, the number of cores, and the size of cache. We're going to look at cache in a bit more detail. And the main components are the control unit, the arithmetic logic unit, and cache. So now we're going to zoom in on the CPU and see what those different components do. As we can see, there's our CPU. We've got our control unit, our cache, and our arithmetic logic unit. So the control unit, also known as the CU for short, it's a major component of the CPU. It's a very important part of the CPU. And it controls the flow of data inside the CPU. So what does the control unit do? It controls. Some of these words make a lot of sense. And they mean what they are called. So we'll look at the Fetch-Decode-Execute cycle in a little bit more detail here because the control unit controls the flow and it controls that cycle. So it copies memory address from PC, the program counter, to the memory address register. And don't worry, we're going to look at these registers in more detail. It then copies instructions or data from the memory address register in main memory to the memory data register, and it increments the program counter. So it's really important for telling the CPU where to fetch instructions from, where to fetch instructions from, where to fetch the next instruction from, where to load the data to. It's also responsible for decoding those instructions. So the instructions held in the MDR, the memory data registers, are going to be translated by the CPU and prepared for the next step. Now the execution part is actually carried out potentially by the arithmetic logic unit, but it could be something like loading data, writing data, or performing a calculation, which you'd use the ALU. And it's a control unit that controls what happens there. So we've already mentioned the next component, which is the arithmetic logic unit. And again, it does what it says on the tin. Arithmetic stands for arithmetics, which is calculation. So computers, At the basic function, all they do is a add, subtract, multiply, and divide. They are doing a combination of calculations on little binary bits, so all the different circuits can change and switch. And it also performs logical operations, so it's performing comparisons like and, or, not, greater than, less than, equal to, not equal to. So the arithmetic logic unit performs calculations, arithmetics, and logical operations. And it stores the results of calculations in the ACC, which is the accumulator. Now, we have looked at the control unit, which controls the flow. We've looked at the arithmetic logic unit, which is responsible for arithmetics and logic. And now we're going to look at these registers. So there's a lot of information here. And what I recommend is to pause this, note this down, and try and use different methods to remember it. So the program counter points and holds the memory address location of the next instruction for each cycle. And it is incremented by the CU after each cycle. So it increases by 1 after each cycle. So once the cycle is complete, we point to the next location. Complete, next location. So the memory address register holds the address of the data or instruction in main memory about to be fetched. So the address from the PC that's pointing to the next instruction is then loaded into the memory address register by the CU. So the MDR, the memory data register, is going to hold the actual data or instruction that the memory address register is pointing to. And finally, if there's a calculation, the results are going to be stored in the accumulator. Now, the features of the registers are they are tiny, tiny, tiny memory locations. They hold a very small amount of data, smaller than cache, way smaller than RAM, and a lot smaller than a secondary storage. So they are small, tiny memory locations that have very fast read and write speeds. Because they're so small, they can read and write data really quickly. And it's also important to note that they are volatile, so the contents are lost when the power is off. And they're an important component of the CPU, and they are also a part of main memory. So we're going to take a look at cache. Now cache, not spelled the same way that we spell cash in terms of money, but it is very expensive. And it holds frequently used data and instructions. So level 1 cache is located right here on the CPU. And it is a component of the CPU. So level 1 cache is used for data and instructions that are frequently used. And it's on the CPU for quick access. So they're not as fast as the registers, but they're definitely faster than level 2 cache, level 3 cache, RAM that was over here as well. They have a very small capacity, and cache size affects the performance of the CPU. Cache memory is expensive, hence it is quite small. So ignore this very small capacity. It has more capacity than the registers, but less than the RAM. I've said the opposite thing there, just so that there's no misunderstandings. Small capacity. It is greater than registers and it is less than RAM. So we've looked at the main components of the computer system that uses the von Neumann's architecture, and we mentioned the Fetch-Decode-Execute cycle. So now we're going to look at it at a little bit more detail. So a computer system takes inputs, and it takes those inputs as an electronic signal, which could be the click of the mouse or the press of a key on your keyboard. Or even me speaking into this microphone right now, that's an input. Now, that input needs to be translated, it needs to be actioned, it needs to be processed, and that is done by the CPU. And we talked about the control unit that controls the flow of instructions. So what the control unit's going to do is it's going to increment the program counter, and that's going to point to the first memory address. And the memory address is going to be loaded into the memory address register, which is pointing to a location in potentially the cache. Now remember, we said that the memory address register is holding the address stored in memory. Now cache holds frequently used instructions, so the first place we're going to look for that instructional data is cache. If it's not there, we're going to try and fetch it from cache level 2. If it's not in cache level 2, we're going to see if we can fetch it from cache level 3. If it's not in cache level 3, we're going to go to RAM. So we fetch data and instructions from RAM, and if it's not in RAM, we're then going to have to go to secondary storage, because it's quite likely that maybe our data and instructions haven't been loaded into RAM. So what we could potentially think about is my input is me double-clicking on my mouse to open up PowerPoint, and my CU is going to control the flow of that instruction. It's going to increment the program counter. It's going to go to the memory address register. The instruction is not in cache. It's not in cache level 2. It's not in cache level 3. It's not in RAM. So we actually need to go to secondary storage, and we need to open up PowerPoint, and PowerPoint is going to be loaded into RAM. And then those instructions are going to be loaded into cache level 3, level 2, level 1. So the most frequently used instructions are in cache level 1. And all of that just to store that tiny piece of data in the memory data register. Now, once that data is in the memory data register, my control unit is going to decide what I can do with it. And it's quite likely I might need to perform an arithmetic logic, either operation, so maths, calculation, or I might need to perform some kind of comparison. And the results of that are going to be stored in the accumulator. Now, all of that is one cycle. That is one fetch, decode, execute cycle. And we mentioned clock speed before, and that happens at a speed measured in frequency called gigahertz. So that happens thousands and thousands and thousands of times per second. So lots and lots and lots and lots and lots of instructions are fetched, decoded, and executed every second, but only one at a time per core. Now, once we've completed that fetch, decode, execute cycle, what will most likely happen is an output is produced. So that could be, for example, the click of my mouse's input. It opens the PowerPoint presentation I'm looking at, and the output is that it is displayed on my screen. So that's been quite a lot of information in regards to computer systems, the von Neumann's architecture, what makes a computer system, how secondary storage, RAM, cache, the control unit, the arithmetic logic unit, and the CPU all work together. Take a look at the video again, make flashcards, go over some exam questions that ask you about components of the CPU, and hopefully this video has been useful and helped you with the upcoming exams.